Today we're going to finish up our discussion of the combined gas law. Let's look at the last couple of examples on our notes. This first example, as we look at this, we're going to follow the same rules. We've got to find what our unknown is. Looks like the final temperature is our unknown, which is going to be our T2. We're going to label everything else. The 235 is our V1, volume in milliliters. 15 degrees Celsius is our T1. Now remember, I told you it'd be a good idea to put plus 273 by that so you don't forget to change that to kelvins. The 784 is our P1. So then the volume expands to 600 milliliters. There's our V2, and the pressure rises to 1500 millimeters of mercury. There's our P2. So writing our equation, P1 V1 over T1 equals P2 V2 over T2. Solving for T2, always an issue when we're solving for temperature, remember. So as soon as you circle temperature as your unknown, you need to remind yourself that you're going to be doing a little bit extra to solve for that. Now, what is never mentioned as far as variables? Well, nothing. Everything is mentioned. All the variables have values in this particular problem. So we're actually dealing now with the combined gas law, and that's what you'll write up beside the problem. Instead of Boyle's law, Charles' law, or Guy-Lussac's law, you'll write combined. So we're solving for T2. Remember, we need to move that to the top first. So getting rid of it over here, we're going to multiply both sides, but remember what the shortcut is, that we're just going to get rid of it here and move it to the top on the other side, since it was on the bottom originally. But now we're still solving for T2, so we've got to get rid of P1, V1, and T1. So both P1 and V1 are on the top, so where are they going to go? We're going to get rid of those and move them to the bottom on the other side. Since T1's on the bottom on this side, we're going to get rid of it and move it to the top on the other side. Redrawing that division line to extend it out a little bit. Double check. We're solving for temperature. Is T on top? Yes, it is. Do we have any P's or V's side by side? Nope. So it looks like we've got a pretty good equation here. So let's rewrite it for T2. P2 is going to be equal to P2 times V2 times T1 over P1 times V1. So let's do the plug and chug part of that equation. Oops. T2 is going to be equal to P2, which we said was 1500 millimeters of mercury. V2, I think you can see now why labeling these at the beginning is advantageous, because there's just so many numbers here. We can get really confused really fast. V2 is our 600 milliliters. And T1 is our 15 plus our 273, so 288 kelvins. On the bottom, we want P1, which is 784 millimeters of mercury, and V1, which is 235 milliliters. So as far as what cancels, looks like we've got millimeters of mercury canceling, milliliters canceling, left with kelvins on top, which is a valid unit for temperature, so we look good there. And we come up with the fact that T2 is equal to 1406.86. Now remember, we can't put this in scientific notation. I'm requiring you to put it in regular notation, but we do need sig figs. And it looks like our 15 degrees Celsius in our original sig figs up there is going to be our limiting value. So 2 sig figs means I'm going to draw the sig fig line here. The 0 that comes next says I don't need to round up, and a lot of people will put down 14 and leave 14. Can we drop any whole number place values? No, we cannot. Those have to be replaced with zeros. So 1400 kelvins is our answer here. So now moving on to the next problem. Says a quantity of a dry gas is a volume of 1.25 liters at 100 degrees Celsius and 880 millimeters of mercury. What would be the volume at STP? Guys, as soon as you see STP, remember that STP stands for standard temperature and pressure. In the past, we memorized that as 0 degrees Celsius and 1 atmosphere, but in all honesty, that in the gas law, standard temperature would be much better remembered as 273 kelvins. And since we've already got 880 millimeters of mercury here, 760 millimeters of mercury is the value we're looking at for STP. Always write those values down whenever you see STP. They're either going to be T1 and P1 or T2 and P2. They're going to be some of your values. So STP, write those values down. We're looking for volume, the new volume, so V2. The 1.25 liters up here, I'm going to erase some stuff off so that it doesn't interfere so much with what we're trying to see. The 1.25 liters is our V1. The 100 degrees Celsius is our T1. Remember what I told you needed to do, plus 273 on that to remind us about that later. The 880 millimeters of mercury is our P1. Those are our original initial values. So now we want the volume at these new values. So it looks like 273 kelvins is going to be our T2 and 760 millimeters of mercury is going to be our P2. I know that you've got at least one problem on your worksheet that's going to involve STP. Maybe as the first values, the ones instead of the twos, hint, hint, but it's going to be there, so watch for that on your assignment. So now let's write our equation, P1V1 over T1 equals P2V2 over T2. We're solving for V2. It's already on the top, which makes it nice. So all we have to do is to get rid of the P2 and the T2. So the P2, since it's on top on this side, is going to move to the bottom on this side. I'm going to draw that line in a little better so it'll be a better separation. T2 is going to, since it's on the bottom on this side, be moved to the top on the other side. So we look, we're solving for V2, so is volume on top? Yes, it is. Here it is right here. And do we have any T's or P's side by side? No, we don't. They're on opposite sides of the division line. So it looks like we've got a good equation. So V2 is going to be equal to T2 P1 V1 over P2 T1. Plug in, chug in the values. Got a little more room down here, so I'm just going to move down. T2 is our 273 kelvins. P1 is our 880 millimeters of mercury. V1 is our 1.25 liters. P2 is our 760 millimeters of mercury. And T1 is our 100 degrees Celsius, but I wrote that plus 273 beside it, so hopefully remembering that that's 373 kelvins. So it looks like kelvins cancel, millimeters of mercury cancel. I'm left with liters on top, which is a valid value for volume, valid unit for volume. So V2 ends up being 1.0593. I look back at my original sig figs and it looks like our 880 is our limiting factor. So it looks like we need 2 sig figs, which means I'm going to draw the sig fig line here. So that becomes 1.1. Now, do I need to replace any of the rest of them? And that is a no, because all of these, none of these are whole number place values. So I just drop them. and this becomes 1.1 liters. And that is the combined gas law.